So yeah, I want to talk to you about a bunch of different things. Logic, circuits, and binary. I don't know if we're going to get to circuits today, but I should probably be able to get to both of these, the first and the last. So let's get started. So yeah, we want to learn how to think logically because that's how computers think. That's how we make good arguments. So that's very important. So let's talk about that. And in logic, things can either be true or false. That's key. All right. So things are either like true, yes, it works, it exists in the real life, something like that, or false, it's a lie, doesn't exist, something's wrong with it. Good argument, bad argument. But I mean, if that's what like is behind logic, true and false, like what does it mean for something to be true? So we need a philosophical lecture again, sadly. So let's go there. What in the world does that mean? All right, what is truth? We can define truth in a bunch of different ways. So, all right, to even approach the definition of truth, we need some new terms. So let's talk about statements. All right, statements are propositions; those are synonyms. So a statement or a proposition, I'll probably say proposition more actually, is a sentence, which is something you can type out or write or say that can be true or false. All right, something that is either true or false is a proposition or a statement. It can't be both. All right, and when I say statement, I mean it's short for logical statement because we're talking about logic today. It's a logical statement. All right, so a statement is a sentence that can be true or false, but it can't be both. It gotta be one or the other. All right, so there are certain sentences that you can write that aren't statements, right? So one of which is this sentence. Right? So if you write this sentence is false. This is not a proposition, and let's figure out why, okay? If it were a proposition, it would either be true or false, all right? If it were a statement, it would either be true or false. So let's try both options. It can either be true or false. Let's see what happens. So if we were to assume that this sentence was a true statement, that means it's telling the truth, right? And it's saying that it's false. And if we were to believe it, then if it were true, it means it must have been false. You see that? And that doesn't make any sense. That's contradictory. So it must have not been true, all right? So it couldn't have been true. So maybe it was false instead. So maybe the sentence was false, all right? So, all right, that means that this sentence is false or is a lie, which would mean that it was telling the truth after all. Do you see that? See that idea? If this was a lie, then it really was telling the truth because it really was false. Right? True. So if it was true, it must have been false. If it was false, it must have been true. There's contradictions in either case. So it can't be either. It's neither true nor false. You see that? It's a contradiction. So, yeah, in either case, whatever we assumed, it didn't work out. So we get a contradiction. And so that's kind of fun. So yeah, sometimes we can't prove stuff, unfortunately. Some sentences aren't even provable. But in a perfect world, we would imagine that it would be nice, right? To be able to just prove all the true things in the world and disprove all the false things, even if you knew it was a proposition. Like, it'd be nice to be able to prove all the true things and disprove all the false things. That's what the mathematicians care about. But sadly, there are even some propositions that are propositions that can't be proven, that we don't know the answer to still, that we may never know. Some things are impossible, so it's kind of cool. But this would be a nice utopia, so maybe we could define truth to be all the things that we could prove. Yeah, that's something. So a bunch of different people scratched their heads for centuries, millennia, trying to come up with the idea of what in the world truth is, what it means for something to be true. And there's a bunch of different competing ideas, all right? So let me tell you a few of them. I am by no means a philosopher. I'm just a lowly computer scientist, but I'll give you a taste of all these ideas of what it means for something to be true. So here's the correspondence theory of truth. This is some things that some people believe, right? So correspondence theorists believe that a statement or a proposition, call it S, it's true if and only if, that's a big logical phrase, if and only if S corresponds to a fact. All right, so they care about facts, something that you could like go and figure out. All right, so maybe, I guess, they're really big on like all the detectives are maybe correspondence theorists. They're like Sherlock Holmes. They're going to take their little magnifying glass and they're going to observe something and then like notice that it checks out. All right, yes, that's a fact. So that must have been true. Okay. But then we have to like define facts, and that just like leads to a bigger rabbit hole. So we're not going to go there. But their idea is that true things correspond with reality. Things that are true are things that I can go look at and touch and feel, and I know that it's a fact. That's what it means for something to be true to a correspondence theorist. All right, maybe that's you. I don't know. So, for example, like this is an easy one. Like, it's true that snow is white, at least in most places, right? That's a true statement because we can go drive up to the mountains right now and observe that reality. Yeah, we can bring our magnifying glass. Okay, does that make sense? It's very vague, very weird, but this is what some people define truth to be. It's true if it's a fact, something I can go and look at. So it's reality. That's what they like. They think there's a correspondence here, right? Facts are my reality. And so here's a silly meme with the same idea, all right? But there's plenty more. There's plenty more ideas. There's plenty more thoughts about what it means for something to be true, all right? Another one is called coherence theory. Let's talk about that. What do the coherence theorists believe? There's actually a bunch of different subtypes of coherence theory, which is a little ugly, but we'll talk about one. So coherence theorists, they're like, a statement S is true because it matches other true things. All right, so it's like a matching game, finding patterns. So here's kind of how a coherence theorist would view the world. They're like, oh yeah, 2 plus 2 is 4. That is a true statement, true proposition, because I can break it down. I know what 2 means. I know what 2 means. I know what 4 means. I know what plus means. I know what the equal sign means. And I can jumble them together, and it all makes sense to me. It matches what I understand about the world. Okay? That's coherence theorist. It matches other true things, and then you can build up new truths from those. There are other kinds of coherence theories. One, a problematic one maybe, is like, a statement S is true because it matches the beliefs of the majority of people in my society. Right? And that just leads to horrible, horrible ideas. Right? So that's probably not the best meaning of truth. But that's what some people have believed, especially historically, right? So you can argue about what it means for something to be true, and maybe you never thought about that. Well, let's talk about a different one. This one's called deflationary theory. This is the one I understand the least, but it's kind of silly. So their idea, if you're a deflationary theorist or a redundancy theorist, you're like, why are we even asking about what truth is? They don't even care. So it's like, it was silly for you to even specify the word truth. There's no need for the word truth. We don't have to specify what truth means, because like you saying 2 plus 2 equals 4 is true was redundant, right? You just use the verb to be. You just say 2 plus 2 equals 4. That is how it is. Okay, there's no need to even use the word truth and define it in the first place. And so that just feels like it's like sidestepping the whole problem. But there are people that think that way. So yeah, but that's another theory, and so maybe you could look into that further and teach me more about it. That's as much as I got out of it. But I'm just trying to show you that the world is not as it seems, right? Maybe even the word truth doesn't have a definition. Doesn't have a definition that everybody agrees on, right? The last kind of truth I want to tell you about is called pragmatic theory. I think it would be useful, or I think utilitarians would love it, because their idea about the pragmatic theorists believe that things are true if they are useful to believe. It's kind of nice. All right, so it's all about the utility. I'm going to believe this thing because it's useful for me to believe it right now, even if it might not actually be true to some other person's definition of truth. It's kind of silly, but interesting at the same time. So like a belief that leads to the best payoff. This is a quote I took from an encyclopedia. Beliefs that lead to the best payoff, that are the best justification of our actions, that promote success. Those are the truth things. Those are truths, according to the pragmatists. Okay? And so a potential way that a pragmatic theorist might believe, a pragmatist might believe, would be that, okay, they'll say that this is a true statement. I will definitely get COVID if I go to that party this weekend. Pretend that this was like during the height of the pandemic. Because maybe they wouldn't get sick, but this is a good pragmatic truth, because maybe like they've got some people at their house that are like immunocompromised or something, and they want to make sure everybody stays healthy. So even though this might not actually happen, they believe that it's true because it's useful for them to believe it, right? It's going to keep their family members safe, something like that. Okay, that's pragmatic theory. And yeah, there's a bunch of definitions of truth. That probably confuses you further. And why wouldn't it? All right? But again, all I'm trying to say here is that there is no right answer, which is, I mean, that makes us uneasy. We've been taught in school that there is one right answer most of the time. There isn't. There isn't in the real world that we're talking about here, okay? In arguments. So, let's talk about logic now. Let's talk about things like this is more mathy. There is one right answer. Let's go back there. That's our safe haven. But now I'm going to say the word true and false, and maybe you should I don't know. Maybe you'll feel less good about it. You'll feel more stressed, but that's okay. We're going to learn about Boolean algebra and truth tables because the goal is trying to tie this back to computer science. Like you speak English, you're given an argument in English, you're writing it down. There's a lot of ambiguity in English text, in English words, phrases, and in any other human language. All right, so it would be nice to be able to formally specify something. That's the phrase. Formally specify something in like a logical language that everybody around the world has agreed upon, so that at least we can get rid of the ambiguity, even if we're not sure about what truth is. Okay, so that's nice. We want to learn how to formally specify our statement so that anybody on any side of the planet would understand. Okay, that they're not ambiguous at all. Let's remove the ambiguity. Okay, and here is a nice leading question. So let's please go to the Written Ice page on our class website, and I'll stop the attendance after we finish it. So do that if you haven't done it yet. Let me clear it out. Feel free to pick. I'll let you get into groups again, of course, and feel free to let's see, what's the word? Like appoint somebody to write down for the group if you'd like. But here's a nice motivating question. So you go to this is the word or. Like there's some ambiguity here. So let's say that you go to a diner and the waiter asks you cream or sugar. That's the phrase, right? It's got the word or in it. And then you're at home. You still live with your parents. Pretend you're a child, and your mom says you can have a cookie or ice cream for dessert. Okay? So please take like a minute or two to say hello to the people next to you. Discuss the difference between the ors in those two sentences because it's not the same or, is it? English is very ambiguous, and please try to write down all the differences you can see. There is a difference, right? All right, take another minute to write down what you're thinking about. All right, that is my timer. Let's come back. Let's see what we're thinking here. Did we notice? Remember to press submit. The first one, you have more freedom of choice. You could ask for both. Yeah, that's the key. Both versus one or the other, but not both. Does everybody, we all notice that? Got an option, one or the other. Option versus one or the other. Okay? We noticed that, I hope. Let me stop that. So yeah, good ideas. I think we got it. Yeah. Okay. We all see it, even if we're pressing submit a little late. So good. So, okay. The waiter is implying that you can totally have both if you want both, right? They'll give you a plate full of both of those things. You can have both. Be a little weird if you meant the other thing, right? And then mom, of course, is trying to lay down the law and saying you get to pick one, right? Pick one, you can't have both. Trying to keep you at least slightly healthy. Okay, so yeah, that's kind of the idea. That means in English, the word or, completely ambiguous. We have no clue unless there's a whole lot of context, right? We have no real clue. Like somebody first learning English, they might think that this means you could have both, right? You might imagine that. So there's really two different kinds of or, but we spell them both or. We can talk about that. We can make a logical symbol for each to make it not ambiguous anymore. All right, that's where we're going with that. So, okay, let's talk about the first kind of or. This was the waiter's or. It's called inclusive or. There's a difference between inclusive or and exclusive or. All right, we'll get to that. So inclusive or, first of all, there's a symbol for it in logic. It looks like a V. That's what it looks like, a little wedge-shaped thing, upside down. But that's what inclusive or looks like. And this is like how it works. All right? Because at the end of the day, you're trying to prove something to be true or false. And so this is a truth table over here. Truth table showing you what the or operation does on every combination of true and false. So this right here is called a truth table. And you can imagine that A is like you can have cream, and B is you can have sugar. All right, and this or is like you can have cream or sugar, like you choosing cream or sugar, or both is possible, right? Cream ORed with sugar. A idea ORed with B. So I guess the idea is like you can OR together two ideas, and each of those individual ideas can either be true or false. Okay, and so like they can both be true. It could be true false, could be false true, could be false false, and then their or, the resulting thing, is either true or false, the final thing. All right, so think of this as think of the A or B as like what you had, like what you could have asked for. Like I had cream or sugar. That's that kind of or again, cream or sugar. It's the inclusive or where it's okay to have both. All right, so this sentence is true. You're not lying if you had both, right? I had cream or sugar. True. The or is true. If I just had cream but I didn't have sugar, it's still a true statement to say this, right? I had cream or sugar. All right. If you didn't have cream but you did have sugar, then it's still, you're not lying to say I had cream or sugar, right? I just had one but not the other. But you're totally allowed to have both. Okay, that was the waiter's kind of or. It's called inclusive or. The only way for it to be false, the only way for you to have been lying, was if you said this, but you didn't actually have cream or sugar at all. You had neither cream nor sugar. That's the only time the or of those two things is false. Okay? So that's a little weird, like combining English and now symbols and shoving them together, but does that make at least a little bit of sense? That's called the inclusive or, and that's the truth table for it. Okay? So that's completely different from the other kind of or. Inclusive or, you're allowed to have both. And so at the end of the day, you're trying to prove something in logic. And so to prove that A or B is true, you just got to prove that you're in one of these three ones, right? You got to prove that you're in one of these, but not the last one. You got to show that either, like what brings you there, you got to show that either A or B is true or both. Alternatively, just show that they're not both false. Okay, so that's inclusive or. There is now exclusive or. And do you see the difference? It's called XOR for short. I'll say that. If I flip between it quickly, do you see the one difference? A and B are just going through all the options, of course. But the exclusive OR versus the inclusive OR, do you see the one line where it's changing? You can't have them both. Can't both be true there. Okay. So the symbol in logic land for exclusive OR is a plus sign with a circle through it. And so you can think of this as like A and B as cookie or ice cream. Okay, this is mom's OR. And then cookie exclusive ORed with ice cream is the final answer. So there's that. And so again, just think of it as like the sentence. I had a cookie or ice cream, or mom's saying you can have cookie or ice cream. And so she does not mean that you can have both. That's the kind of or she's talking about, right? You can't have a cookie and ice cream. Can't have them both. Can't both be true. But this is what you can choose from. You can choose from these two options, right? You can have a cookie or ice cream, and mom was telling the truth, right? About that kind of or. You can have the cookie but not the ice cream, or you can have the ice cream but not the cookie. That's what it means, okay? So that's the only difference is this one. They can't both be true, all right? So with that in mind, again, you can think of like a sentence, like mom says I can have a cookie or ice cream. And falsehood is, I want you to think about false, the idea of something being false, as if someone was lying to you. That's the easiest way to understand it. Someone was lying. So for example, this or that makes more sense, like I had cream or sugar. We were only lying if we had neither, right? That's what it means for the answer to be false, okay? For exclusive or, mom was lying to us if we actually could have both. She didn't imply it like that. Or if we didn't end up having any of them, like we got in trouble or something. Mom still lied to us saying we'd have cookie or ice cream. I got none of them. So that's that one. So to prove, again, you're trying to prove that something's true. To prove that the exclusive or between two things is true, you got to prove that you have either A or B. One of them is true, but not the other. That forces you in one of these true categories. Okay? Again, it's just a bunch of symbols right now. They'll make more sense with examples. So, yeah, that's exclusive or. That one, a little weird. This one probably makes the most sense. Maybe I should have started with it, but the ors went along with our example. This one's called and is pretty much, and isn't really ambiguous in English. The symbol for and in logic is the upside down or. It's like a wedge-shaped thing. So it's almost like an A without the little dash through it. And then the and is like you have one thing and another. So to prove that A and B, the and of A and B are true, you've got to show that they're both true. That's the only one way that it gets to be true. Okay. So again, you can say that like this is cream and sugar. Maybe like this is A anded with B, the logical symbol there. And you could say that like we have. Let's talk about this sentence. Let's come up with this idea. Let's say the waiter is saying we have cream and sugar for you to choose from. So there's an and in the sentence. So this is the logical and it's only true. The waiter was only not lying to you if really they did have cream or sugar for you to consume. Yeah. The waiter was lying to you. It's not true if there was cream but no sugar. If they were really out of sugar, it was false. It was a lie to say that we have cream and sugar. You see that? That's what's going on there. It was also a lie to say we have cream and sugar when there wasn't any cream, but there was sugar. So it's still a false statement. And then, of course, this is just a big fat lie if you had neither cream nor sugar and the waiter said to you, we have cream and sugar. The only way for it to be true is if there really was cream and sugar in the back, both of them. Okay, that's the idea. So again, to prove something, to prove an and of two things is true, to prove A anded with B is true, you got to show that A is true and also B. You got to prove them both individually. They both have to be true at the same time for the and to be true. Okay. Any questions about that? Hopefully the tables at least are getting a bit easier to look at. This is just every combination of true and false over here, and this is like what the output is of the and operation. Okay. Next, probably the simplest one because it only works on one thing. It's called not, or logical negation, we say. And this symbol it looks like this. I think of it as like a diving board, That's how I teach my CSCI 26 students it. Because it's like a person is about to jump off and do a flip, because what negation does is it flips true to false and false to true. Okay? That's the idea. So, this is like the waiter saying, we don't have cream. Okay? And where that means A is cream, and we're trying to say that not cream is true. Do you see that? Not cream is a true statement. That's only true if they really didn't have any cream. You see that? It's flipping it. False becomes true, true becomes false. With the negation, that's what's going on there. And so if you want to prove that the not of something is true, you want to prove that the negation of A is true, you have to show that A was false to begin with, because that's the only way its negation was true. Okay? That's what's going on there. So there's only one way to make it true, and the negation just works on one thing. It's not combining things. Oops. What did I just do? There. Back to normal. Okay. So yeah, it just works on one thing, whereas these ones, like, they combine two things into a bigger thing. The not just takes one thing, negates it. Alright. So one cool thing I can tell you right now is a combination of inclusive or, and not will build you any truth table you want. So if you have, like, let's pretend you've got a statement with a bunch of, like, or you've got a bunch of variables, a bunch of logical variables, A, B, C, D, all the way to however many you want, and all their combinations, you list them out, and you have some goal in your mind. You're like, I don't know what this cloud of a goal is, but, like, I want it to be true in this case, and false in this case, and false in this case, and true in this case, and false and true. And you can come up with whatever ordering you want, whatever combination of things you want. Like, I'd like the output to be always like this. Just using these variables, and, inclusive or, and not, combining them all together, you can build any right-hand side. You can build any final answer truth table that you want, which is really powerful. And so there's a very big correspondence between outputs of a truth table, like some logical formula, and computation. So if you just make little tiny circuitry for and, inclusive or, not, you can build a computer, pretty much. That's kind of where we're going with this, in a sense. That's pretty nice. But yeah, let me prove that to you. Let me have you prove it to yourself, actually. So here is, well, if this is actually a true statement, this fact is true and I'm not lying to you, then that means exclusive or, which is like another thing, right? I said you can make anything with and, inclusive or, and not. Exclusive or is none of that. So that means you must be able to represent exclusive or of A and B just using some combination of and, or, and not, the inclusive version. So you try, all right? I'll give you the answer, but I want you to fill in the truth table to show it, all right? So here's the answer. A exclusive or with B, that's equivalent to not A and B ORed with A and not B. Okay? Interesting. So what I want you to do is try to fill in this table. I'll get you started. All right? So the variables involved are A and B. But I legitimately want you to try this. This is a very good thing for you to try. And then I'm going to, like, put a bunch of stuff over here. Try to draw the straightest line I can. Whee! So A and B, what are the combinations of them? The standard order is like this. True, 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 false, false, true, false, false. Those are the only combinations of A and B, because they could be true and false. Now, I want you to build up the truth table for exclusive or already. That's on a different slide. I want you to try to build up this guy, this or of this with this. And so you have some intermediate pieces, right? You're going to have to figure out what is the not A for every case, because you need that to build the not A ANDed with B, right? And then you also need the not B to build the A ANDed with not B. So maybe you need the negation of both of them. Like, fill out what that means. And then, now once you have the negation, you can use the and to make the not A ANDed with B and the A ANDed with not B. And then finally, once you have those, you can OR together their answers to get the final thing. The not A ANDed with B, ORed with A ANDed with not B. All right? So it's a little disgusting. I'm going to give you these tables in a lot of time. or at least I'll give you a head start. But like for this one, for example, here's how you compute this. So the negation of something, right, was to flip the true to false and the false to true. So in this case, I'm trying to like fill in what should go here for not A. You look at the A column and you run the negation on it. So it was true. So the negation of true, not true, becomes false. You see that? So I'm going to put a false here because A was true. What goes here if A is true? False again. If A is false in this case, what do I put here? True. If A is false in this case, what do I put here? True. So that's the not A column. All right? Does that make sense? So you're going to do the same for all these, building them up slowly but surely. And here is, I'll give you all the truth tables. So please help each other and give this a try. See if you can fill out this truth table. I'll have to make these pretty small, sorry. You can always come up to the screen and look at them if you need to. There's or, here's and. Let's see if you can do as much as you can. I believe in you. And then not flips them. Those are all the pieces. See if you can come up with the final thing on the right. The final combination of truth values there. So give that a try. Plug them in. You know the left side is this, the right side is this, the output's that. Try to read it off the table. So for example, if you're working on this one, not A and with B, you got the not A, the false, and with the B in this case would be true. So just go look it up. All right, false and with true. Okay, the output for there would be false. Remember the order though. Thing on the left and the thing on the right. It might be out of order of the column. I think we've scratched our heads enough on it by now. Might be confusing, but hopefully you can kind of see it. Let me do it with you now. I guess I kind of need these up here. Let me consult them with you. Here they are. Whee! So this guy, for example, B, we got, all right, true becomes false and false becomes true. So it's just going to be what? False, true, good. This is the ground truth, the A and the B. We're assuming A and B are those things, then use them for the rest, all right? And now that I have the not A, I have the B already, I can AND them together. So not A and B, let me fill in this column, for example. What is going to go here? It's going to be, all right, the false ANDed with true. False ANDed with true. So that is, I look it up in the table, false ANDed with true is false. See that? So I put a false there. And then here, and again, it's not AND with B, so it's going to be this guy, false ANDed with true again. It's still false. The only way to make true with AND is if they're both true. Yeah? And then we have true ANDed with false. Or sorry, true ANDed with true right there. That one works. That's true, right? True ANDed with true. And then we have one more. Not A is true, ended with false. Again, one side was false, the whole thing's false. See how I'm reading that? Did I mess that up at all? False. Yeah, I think that's fine. And then this one again. A ended with not B. So again, you have A, you have the not B, so let's add them together. True ended with false. That's false. True ended with true. Ooh, that one's true. That's the only way to make it true if they're both true. False ended with anything. Always false. False ended with anything. Always false. Okay? So kind of the secret is like, you know that exclusive OR has a true in this column and this column. Do you see how like this one picks out the third one, this picks out the second one? Then we're ORing them together right now. So now I can OR them together. And so I'm ORing these now. So false ORed with false, sadly still false. Darn. It's the only way for it to be false. This one's false ORed with true. That one's true, good. Because one side is true. It's very easy to make true with an OR. Very hard to make true with an AND. True ORed with false, true. And then false ORed with false, false again. And so what do you know? If I delete these now, you go to exclusive OR. It is false, true, true, false for those exact combinations of A and B. We have just proved, beyond a shadow of a doubt, that A exclusive ORed B. A exclusive ORed with B, which we knew already was false, true, true, false. See how under the same ideas, it's always the same answer? It's equal, 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 equal. So they're the same formula. They're doing the same thing. They work the same way with the same combination of values. So that means because these columns are equal to one another, it works the same way. This is just another way of writing that. See that? That's how we prove it. That's one way to prove that they're equivalent things. It's kind of cool. So yeah, you can use and inclusive or and not to compute anything, to make any right-hand side final truth table that you care about. Which is really powerful, really cool concept. You can actually go further than that. As you make CPUs, it's a lot cheaper to just mass produce one kind of logical operation circuit. And so some very smart people came up with some more operations that are even cooler. One is called NAND, the other is called NOR. And so they're a combination, of course, of what we already know, because you can make anything with our AND or not. So NAND, the operation called NAND, does A AND with B first and then negates it. Right? So here's A and B, here's their AND them together, and then here's the NAND, just negate whatever was the AND. Okay? So that's NAND, and then NOR is kind of the same as the negation of A ORed with B. So here's the OR, here's the negation of that. That's NOR, A NOR B. Okay? So those are some silly operations. But these guys are what are called functionally complete by themselves. All right? So what I told you here, saying that and or not can express any truth table, that's what it means to be functionally complete. All right? So if you use some combination of and or and not, you can use those to make anything. Those are functionally complete. You can make any truth table. The cool thing about NAND and NOR is they are functionally complete by themselves. So NAND, just NAND, is functionally complete. Which is really cool. Same with NOR. Just NOR by itself is functionally complete. You can use just a bunch of NORs in some weird combination. You can make any truth table. Which eventually we'll learn leads to making any kind of computation. So you can build a computer out of just NANDs, is where I'm trying to go with this. And that's cheaper, because like you go to the, I don't know, you go to the logical operation Costco, you can just buy in bulk a bunch of NANDs. It's much better than just buying a bunch, like a few ANDs, a few ORs, and a few NOTs, okay? That's the idea. You can make anything out of just NAND. You can make anything out of just NOR. That's really, really fancy, okay? So, yeah, that's a bunch of truth tables. That's a bunch of symbols. Are there any questions about any of that? So I want to introduce, I think, one, let's see. Just want to do some word problems now. Try and get this in our minds. So, okay, here is an idea, like, here's English, and again, English is ambiguous. The whole goal is to translate this to logic, right, so that we can prove it easier and understand it better. So like here, I don't know, maybe this is Dad. Dad tells us, I'll give you $20 if you clean the bathroom and mow the lawn or do the dishes. And those two things are within some outer parentheses there. All right. So we are lazy children, and we want to know, like, what are the minimum conditions necessary for us to get $20? Okay, so this is logic in real life. Apply it. Okay, so let's introduce some symbols because we've been learning all these operations with just symbols. Let's say that clean the bathroom is A. Let's say that mow the lawn is B, and let's say that do the dishes is C. So really, the form of this kind of argument or logical statement that Dad is making is like, all right, you got to do A and B or C. See how I'm translating that? That's what's going on. And so our goal as lazy children is to like get the $20 and do the least amount of things. Okay, so we can make, like, this is the operation that Dad wants us to perform. This has been guaranteed to be true for us. So we want to figure out under what conditions, what combinations of A, B, and C, being true or false, will we get $20. We're guaranteed to get $20. Okay? So the goal is to make a truth table. Let's make a truth table for that formula. All right, so bathroom is A, lawn is B, dishes is C. And so we're trying to make a truth table for A and B or C. Oops. This is finally one with 3 logical variables. All right, so we have to make columns for A, B, and C. And we're not sure what they are yet. We're trying to figure out which ones like give us the best payout for the least amount of work. So you have to try every possibility for A, B, and C. So there's 2 options for A, right? It could be true or false. 2 options for B. Same with C. It all either be true or false. And so there's 8 total options for their combination. You start multiplying, okay? So, all right, the standard order, there's always an order. If you know binary, it's binary counting down. But the standard order is this one flips all the time. True, false, true, false, true, false. The last one always flips. True, false. And then this one flips half the time. So it stays true a little bit longer, stays false a little bit longer. True, true, false, false. True, true, false, false. This is an easy way to come up with every possibility. I'm not going to have you memorize this, though. Eventually, it'll become useful. And then this one just stays, all right, this goes and stays true even twice longer than that one. So it stays true 4 times. True, 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 true. Stays false even longer. False, 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 false. And this is every possibility. It's an easy way to come up with every possibility of true and false for 3 things. And, all right, now I want to build the formula for this. Maybe an intermediate place to stop is the B ORed with C. So I'll do B ORed with C. Then that will let me, once I can AND that with my A and get my final answer. AND with B ORed with C. All right, and this will help us list our options. So what's B ORed with C here? Remember that OR is true if any of them are true. So true ORed with true, true. True ORed with false, still true. False ORed with true, doesn't matter where the true is, still true. False ORed with false, so that's the one way to make it false, sadly. So there's a false there. And then similarly, you got a true somewhere in each of these 3, so put a true 3 times. And then finally, false ORed with false. It's the only way to make an OR false. Cool. All right, and now I can take this, and I can AND them together to get the final thing that I cared about. Again, talking about this stuff. So, okay, true ANDed with true, that is true. That's the only way to make an AND true, remember. You got to both be true for the final answer to be true. Any other combination, any false anywhere, the whole thing's false. Ruins the party. So, okay, A, true ANDed with true again. True. Cool. True ANDed with true again. Nice. True. So these are all ways for us to get $20, right? And then finally, we got true ANDed with false. Oh no. So one of those is false. So we got false, sadly. And then over here, A ANDed with B or C. A is false in all of these guys, so it's going to force everybody to be false. Okay, for those last 4. False, 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 false. So these are the 3 combinations of ways for us to make $20, and now we can sit down and like scheme because we want to do the least amount of work. So we'll get $20 if we clean the bathroom and mow the lawn and do the dishes. Dad will give us $20, but that's more work than we needed to do, right? Here are 2 other options. So we are forced to always clean the bathroom. You see that? We are forced to always clean the bathroom, but we can pick our choice of mow the lawn or do the dishes, and we'll still get the $20. That's what it's trying to say. See how the truth table is proving that to you? And you can do this for something more complicated, and it will make it easier on your mind. So now you see, all right, we're forced to clean the bathroom, but we could either mow the lawn and get our $20, or we could do the dishes after cleaning the bathroom and also get our $20. Okay, does that make sense, Jess? That's how you create a truth table out of things, and it gets a little bit large once you have multiple variables involved, but I think that makes enough sense. All right, so let's say you did the same thing. Dad told you to do something different. And here is what it came out to be, with symbols at least. A ANDed with B, ORed with B, ANDed with not C. Okay? So all those things is what you're trying to do. And so, again, I got A, B, and C. I'll list out all their options for you so that we all have the same order. And then I want you to try the intermediate steps. All right? What's in between here? You got... well, you have A and B, so you can create the ANDed with B very easily. Then you got that side. And then for this one, you need not C. So you need not C. You column for that, just to start it off. Get you ready. To do the B ANDed with not C after that, you're ready. B ANDed with not C, got them both. And then finally, you got this one, you got this one. You can finally do their OR. You can do A ANDed with B, ORed with B ANDed with not C. Just like that. All right, so let me give you the order. We got true, false, true, false, true, false, true, false. This one stays true twice as long. True, true, false, false, true, true, false, false. This one stays true twice as long as that. True, 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 true. False, 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 false. That's meant to be an F right there. Let me erase and try again. And then I'll try to paste those pictures again so that you have them. Dun, dun, dun. So here's and. And PowerPoint is very slow. And then let me give you OR as well. It's inclusive OR. And then I can't speak. Negation just flips things. Okay, not or negation just flips from true to false and from false to true. So give that a try. Give you like a minute or two head start. And see if you can get the final column. Figure out all the ways that it's true, because maybe that's going to make you money or something. This is what computers are very good at. So, all right, let me do it with you now. We'll figure it out together. So, all right, A ANDed with B, we know that one. So true ANDed with true, that's going to make it true there. And then it looks like I got true ANDed with true again. Cool, got true again. And then we have true, false, true, false. Darn. So we get false there. I believe, yeah, now A after that is always false, so it doesn't matter. So everybody's false after that. So that's A ANDed with B. So there's two ways to make it true for these combinations. Where A and B both have to be true, of course. And then C, not C, the negation of C is just flip it. So here it was true, then it'll be false. Here it was false, now it'll be true. I'll just do that a bunch of times. False, true, false, true, false, true, false, true. Trying to keep it in a line. And then now that I have not C, I can AND it with B. So I take these two columns and I AND them. So I got true AND with false, sadly false. True AND with true. Ooh, that one's true. Cool. True. Then I got B is false in both of these, so not C is unhelpful here, so it'll be false twice. And then for these two, B is true, so cool. Now it's not C telling us what the answer is, so if it's false, it's false. If it's true, the whole thing's true. And then finally here for these last two, the B side is false, so it's forcing everything to be false. Okay? And then for the last one, I just take these two guys, which I made, and I OR them together. All right, so it's true if any of them are true. So true ORed with false. Cool, that one's true. True OR with true, yeah, that works out. And now do you see how the rest of these A and with B are false? So, like, the answer depends on this guy always now. It's true if that one's true. Because I know the other ones, A and with B, is not helpful. It's not going to give me any truth. So, all right, it looks like it's true just with this one. See that? That's how I figured that out quickly. And then the rest are all false. False, 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 false. So hopefully we kind of see how it's working. We got close to that, if not perfectly that. And maybe this is a lucrative endeavor for us. And we noticed that there's 3 ways to make this final thing look true. And I'm going to try and keep the T visible. There we go. True, true, true. There's 3 ways. Either you can do A, B, and C all together, or you can do just A and B but not C, or you can do neither A nor C, but you just do B by itself. Maybe that's the easiest way to get your money or something. That's telling you how to do it. Okay. Any questions about that? How I made it? How I filled it out? How I noticed the intermediate steps? All right. Okay, we do have time to get to circuits today. I'm happy. So, where I'm going with this is computer science, right? So, deep down, computers are thinking logically. They're very, very smart but very dumb, and so they're thinking in this way. They're doing ands and ors and nots all day long, and that's creating computation. All right, I'm gonna try and answer this for you. Like how is all this fun stuff? I like pushing these symbols around, but where does it get me? Well, it gets you to build a computer, all right? Because all a computer is a bunch of ands, ors, and nots, or really just nands. But a bunch of ands, ors, and nots, easier for humans to think of it that way. And you make some symbols for them, and you just wire together all these symbols, which are called logic gates. And then just with a bunch of these combined in a weird way, plus a clock signal that goes high and low voltage all day long, that gives you just those 2 pieces you need that are all that you need to build a computer. All right, so here are your logic gates. All right, so what we're doing is we're pushing around information inside of a computer. We're pushing around ones and zeros, and what are ones and zeros but trues and falses? So true is like a 1 is like high voltage inside of a computer. Your 5 volts or whatever. And false is your 0. In binary land, it's just low voltage inside of a computer. It's like 0 volts. And so here are the gates. All right. You read it like information is flowing from left to right, but you can arrange these in any way. There's an order to it. So here's like wires. You've got input wires. You can feed in a 1, feed in a 0, feed in a true, feed it in a false, and this is the AND gate, we say. So the output of this Q, is A and with B, whatever it happened to be. Okay. That's the output of this AND gate, and that's that one. All right. So I remember it because it looks like that bullet thing from Super Mario. So that's the AND gate, and the OR is like the curvy version. So it's this computes the OR of A and B. So it's got like curves there. It's got a point there. That's how you remember the difference between AND and OR. And then all I really want you to remember about are these ones. The other ones are a little bit more complicated, but we know that those can build anything. So this is inclusive OR. And then this is called the NOT gate, or it's also called an inverter. And so output from there is not A. And so I want you to think of to understand the others, think of the little dot there as where the negation happens. This is just passing along the idea. passing along A, and then it negates it right there at that dot. That'll help you understand NAND and NOR. Because NAND, what is NAND? It's first do the AND, then do the negation. This is the symbol for it. You see it? First do the AND, feed it through the AND, then negate it. That computes the NAND. This computes the NOR. First do the NOR, then do the negation. And then there's an exclusive OR gate where you just take an OR gate and just put another little slash there. That's how you draw the exclusive OR gate. Okay? So let's say we have some computation that we want done. We want to build a computer to do that computation for us quickly. Let's say that like this is the logical formula we'd like our computer to compute. The result of not A and B ORed with C and not D, right? So I'm going to use my gates to make this happen. I'll make them small so that we can look at them. But here's how you do it. Here's how let's come up with the schematic that we can then go and build if we're an engineer. So we got 4 variable inputs, right? So we need 4 wires coming in with A, B, C, and D. Whatever they were, the high, the low voltages. Those 4 wires coming into us, okay? Feeding our information, whatever they were. And then our goal is to like jumble them all together in some box and come up with an output wire with the answer. All right, so let's try to do this side. Let's do not A and with B. All right, so the first thing I need to do, what's the computational stages of this? Like I need not A before I can AND it with the B, right? So the very first step for this side is the NOT gate or the inverter. I'm going to take A, I'm going to flip it with a NOT gate. So now I've got not A coming out of here. See that? And then I can feed it into an AND gate now because I got B already. And I'll take the 2 things and AND them. So I'll draw the little bullet looking thing. And now I've got not A ANDed with B. See that? So this is not A ANDed with B coming out of that wire now. And so let's do the other side. C ANDed with not D. So again, I want to invert the D. So this is not D coming out of there. And then I've got, I'm going to send that also to an AND gate. Boop. And so coming out of here, I've got C ANDed with not D. Okay? And then our final answer is take those 2 things and OR them together. See, so we need an OR gate. So we'll draw that in. Boop, 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 something like that. I can never get these to align properly, but you get the idea. It's supposed to be a pointy thing there. So there's my OR gate, and I can feed these 2 in, and that gives me my final answer. Because coming out of there is just those 2 things, which we know what they were, ORed together with inclusive OR. And so I got my not A and with B, ORed with my C and with not D. Are you reading it the way I'm reading it? Good. Do yell at me if you have any questions about this stuff. Because this is kind of cool. Like you can figure out the order. You can make a computer like you flip some switches for A, B, C, and D, and then it lights up a light if it's true. It doesn't light up a light if it's false. Like you do that if you're an engineer. That would be like your first engineering class or something. So that's kind of nice. And then this all generalizes to be computers. So here you try. Here is a formula for you. B or not C AND with not A and D. So draw the wires, bring them together, and get the final output looking like this, and help each other. Give you a few minutes to try it, and then I'll do it with you. Give you like 3 minutes to try it. And here, let me give you my other answer over here, just like as a side. So if you wanted to see how the final thing should kind of eventually look. Something like that. So maybe it's not the best to have A, B, then C, then D in that order of wires. All right, that's my timer. Let's see. Let's see if you're thinking what I'm thinking. And honestly, it might be better to write the B wire next to the C wire and the A wire next to the D wire. But I'm just going to write them in order. We'll do it live. So A, B, C, and D. Why not? And then, all right, I need both sides of this because those are the smaller things that I eventually need to AND together. So I want B ORed with not C. So I got my B. And I'm going to need not C. I'll use an inverter. I'll use the NOT gate to get that. And then I want to OR them together. So I'll introduce an OR gate in between here. Right? Boop. Boop. And so that's going to, coming out of here, is my B ORed with not C. Okay? And then, all right, I need not A and with D. So I need to negate the A, the NOT gate, or an inverter. And I need to use an AND gate to AND it together with whatever D was. So I need to, like, I don't know, let's bring it down here maybe, AND it together. And then I've run out of room, so I'll delete this now. Whee! Bring it over here. There's my AND gate. And so I want, like, I don't know. Because you got the B ORed with the not C, it's like going this way, and like the A is going here. Like, you don't want it to touch the wire, right? So people do this in the schematics. If the wires are touching, you put a little circle, and they get to cross. We don't like that. And so if you want to just show that the wires shouldn't touch, like don't have it contribute anything, this is kind of cute. You just show it like, boop, like that. You draw it hopping over the wire. So there's that. So there's not A and with D. So now coming out of here is not A and with D. And then finally, I want to take those two pieces that I have now, and I want to AND them together. So I'll use an AND gate one last time. Take those two pieces, and it will spit out my answer. There's the answer coming out of there. I'll just call it answer. I don't want to write it out. So that's the idea. Is that kind of what we got? Any questions about that? How you draw it? How you think about the order? Just like do the parentheses first, I guess. That's kind of how it works. All right, with that, with the remaining time we have, which is not too much, like 10 minutes, I would like to talk to you about binary, because that's like the third thing, right? You got voltages being passed around in your gates. You've got trues and falses being worried about in logic land and symbol land. The last piece of the puzzle is the ones and the zeros, right? That's what computers think with. How does it all work together? So let's talk about binary now, right? It's like that. I'll try to answer this. Like you've heard about the ones and zeros thing. I've been saying the words before, saying the phrase. How does that apply to our discussion? So again, 1 is true, 0 is false. You can think about that like that. And our computers, inside of a computer, there's nothing but logic gates and like a clock circuit secretly. So it's mostly logic gates. 1 is true and 0 is false. And like every piece of information, remember, is stored in binary format, stored in terms of ones and zeros, and our logical operations inside of our logic gates have to do like addition on like 2 numbers that I saved in my computer, or like somehow convert the image file into pixels on my screen just by sending information, which is ones and zeros, through logic gates eventually to some output form. So that's pretty cool. So let's learn about binary, because that's a number system consisting of ones and zeros. All right. Here's the last slide I want to show us today. So binary is a new number system. All right, so let's talk about our own number system first. Our number system is called base 10. That's what we think in as humans. It's called decimals. Decimal number system. Hopefully you've heard that word before. So our numbers are decimal numbers. Okay? And so that means it's also called base 10 for a reason. Decimal, you got like the Greek word for 10 up in there anyway. So a decimal number, right, the numbers that we know and love, are made up of 10 digits total. 1, 2, 3, all the way to 9, right? All those numbers. And that's 10 digits total. So that's why it's called base 10. 10 digits. Okay? And so like you have 9, you try to add 1 to it, you're going to end up with the number 10 because you've run out of digits. Do you see that? I'm going to be introducing new bases to you right now. Like binary is called base 2. We were thinking in base 10. And so there might be ambiguity. And so I'm going to use a subscript to write numbers in a certain base. This means 10 in base 10. 10, the decimal number we know, not 1, 0 in binary or something. Right? So like you can write 123. That's my decimal number, 123. That's me using the subscript notation to say this is a number. I'm writing it in base 10 right now. the number system that we know and love. And we think that we chose the decimal number system because we as humans have 10 fingers. And so we think in base 10, probably because of that. And so maybe if you lived in the Simpsons world, you'd be thinking in base 8. But binary is a different number system. It's base 2. And so that implies you only have 2 digits to work with. And we know what those are, right? That's your 0 and your 1. So binary is a number system where you only have 0 and 1 to work with, right? And so that means, like, you list all the numbers, you try to add 1 to 1, you've run out of digits in binary to keep it in the same place. You have to make a new place. So that implies that in binary, the number 2 must be 1, 0. And it's not 10, it's 1, 0, base 2. You see how I'm writing that? So this is not the number 10 decimal, it's the number 2 in binary. Okay? That's how I'm going to specify. That's what I'm doing there. That's where I'm going with it. And each digit in a binary number is called a bit because it's short for binary digit. We didn't want to say all that, so we made it short. So for example, this number, whatever it is, 101101, that has 6 binary digits. This is a binary number with a base 2. I have to specify that. So this is a 6-bit number. And I'll eventually tell you which number it is in decimal. I'll tell you how to convert. A byte, by the way, is an 8-bit binary number. So if you take 8 bits and you jumble them together, that becomes a unit of space inside of a computer. It's 1 byte worth of storage to save that many things. All right, and so this corresponds to numbers. And just keep the subscripts in mind because, like, 1011 in binary is absolutely not the same as 1011 in decimal, right? This is the number 1011, and this is the number 11, I think. Yeah, this is the number 11 in decimal. It's not the same as 1011. It's much smaller. So you have fewer digits to work with, right? And I'll teach you how to think in binary. I'll teach you how to convert. But, like, you can imagine that, like, if this is the number 2 in binary, then the number 3 must be 1, 1. And then you've run out of, right, plus 1. And then you've run out of digits again. If you want to add 1 to that, and that's the number 3 in binary. What must the number 4 in binary be then? It's got to be 1, 0, 0. You have to add a new place in. See that? Another plus 1. So that's a little trippy. But you'll get it soon enough. And that's, I think, what I wanted to say. Any questions about that? So it's a brand new number system. Binary. Base 2. Only 2 digits to work with. And we'll have to wait until next time to learn about how to convert between binary and decimal. All right. So I think that's all that I wanted to do today. Let's make sure I'm not releasing anything right now. No, I'll save your next programming assignment for the programming lecture. So that's all that I got for us.